Okay, so let's look at another example of mathematical induction. We'll continue mathematical induction in this class also. In the next class, I'll most likely give you a Python assignment based on mathematical induction. So we're going to prove this identity today, right? So again, the idea is that you start with a base case, right? And then you do the inductive step. So there are two steps involved. And in this case, we're going to again start with the left-hand side and show that left-hand side gives you the same result as the right-hand side. So let's look at the base case. Again, the base case is when n is equal to 1. So this is your n, right? So you set n equals 1 on both the left-hand side and the right-hand side, and then you show that they both give you the same answer. So when you plug in n equals 1 on the left-hand side, so this is again your left-hand side, right? So when you plug in j equals 1, you get 0 as the answer. So it's just 1 minus 1 equals 0. And then on the right-hand side, right, you get that, and so you plug in n equals 1, you also get 0. So again, you have shown that your left-hand side and right-hand side are both equal to each other. They both give you 0 for the base case. So you're done with the base case. Now, again, this step, the inductive step, is tricky, right? It involves some subtle steps and then some algebra also. So again, we say that our statement, our mathematical theorem, is true for n equals k, right? So we replace n with k, right? So the statement or the equation that is given, you replace n with k in that. So that's a statement that we're going to use, and then you have to prove this, right? That it's true for n equals k plus 1. Again, we say that it's true for n equals k, then it must be true for n equals k plus 1. So, but this we have to prove this, right? Now, again, we start with the left-hand side, right? So this is our left-hand side of this equation, right? And again, that step where you have to separate out the last term. The last term is again when j is equal to k plus 1. J is equal to k plus 1 is the last term, right? So you again take this factor and then plug in j equals k plus 1. So when you plug in j equals k plus 1 in this, you get j times j minus 1 is going to become k plus 1, right? J is k plus 1, and then k plus 1 minus 1. So for this part, you just get k. So j into j minus 1 give you k times k plus 1. So this is what you get. So this is your last term. Now again, why do we do that? Because we have to use the inductive hypothesis that our statement is true for n equals k, and so we plug in this equation, and so this whole sum becomes equal to that, and so after this, it's all algebra, as I said last time also. So let's go through the steps. Again, it's going to involve a lot of factorization in these steps. So first we make the denominators common, right? So the denominators are common. You bring the terms together, and so this is you get 3 times k plus 1 times k over here. So now you replace k squared minus 1. So remember that k squared minus 1 is equal to k minus 1 multiplied by k plus 1, right? So this is k minus 1. So then you can see that there's a common factor over here, right? K plus 1 is common over here, and in this term also. So you factor these two out, and this is what you get. So you factor these out, you're left with k, and then k minus 1 over here, and then 3 times k over here. And so now you have to simplify this term in the bracket. And so this is, you multiply k in, this one becomes k squared, this is k, so k squared minus k plus 3k, 3k minus k is 2k, and so you can see that now you can write k squared. Now the whole idea is to write it in a form, bring it in this form, right? You have to simplify and bring it in this form. And so when you get to this step, it's obviously not in that form. So what you can do is you can write k squared plus 2k as k squared plus 2k plus 1 and then minus 1. And so k squared plus 2k plus 1 is k plus 1 whole squared and minus 1. And so this is what you have in this step. And so now we can see that we have this. This is just our right hand side, right? And so we started again with the left hand side and we get the right hand side. So this means that it's proved, right? The theorem is proved. Okay, go ahead and solve the worksheet. Let me know if you have any questions.